Right now, while you're hearing this voice, something is happening beneath your feet. Something slow, something ancient, something that has been going on since before your country existed, before your continent took its current shape, before the oceans filled their basins. Deep inside the planet, trillions upon trillions of atoms are quietly tearing themselves apart. Not in an explosion, not in a flash of light, just slowly, inevitably. One by one, in absolute silence, they shed pieces of themselves and transform into something else. And they have been doing this for longer than life has existed on Earth, longer than the moon has circled above us, longer than the oldest rock you could hold in your hand. This is not a metaphor, this is physics, and it is happening right now, under every city, under every ocean, under every mountain range on this planet. There is a slow fire burning at the center of the world, and it has never gone out. Not once in 4.5 billion years. I want to tell you about the element responsible. Not because it made a bomb, not because it lights up reactors. Those are chapters in the middle of a much, much larger story. I want to start at the real beginning. Not in a laboratory, not in a mine, not even on this planet. I want to start in the darkness between galaxies, where two dead stars were falling toward each other at a fraction of the speed of light, and the universe was about to do something it only does in the most violent moments of its existence. Because that is where our story truly begins. That is where element number 92 was born. Its name is uranium. And before we understand what humanity did with it, we need to understand what the cosmos spent billions of years building. Most people, if they think about uranium at all, think about one of two things: a mushroom cloud or a cooling tower. Maybe a yellow warning sign with 3 triangles. That association is understandable. It is also incomplete in a way that does almost everything about this element a serious injustice. Because uranium is not primarily a weapon or a fuel source, it is, first and foremost, a piece of cosmic architecture. A fragment of stellar catastrophe that traveled across unimaginable distances and settled quietly into the rock beneath our feet. The story of uranium is the story of the universe learning to build something heavier than iron, and that lesson required the most dramatic classroom imaginable. In 2017, on August 17th, instruments around the world detected something extraordinary. A ripple in space-time itself, a gravitational wave washing through the fabric of the universe like a tremor through still water. Astronomers scrambled to point telescopes at the source. What they found confirmed a theory that had existed for decades but had never been directly observed. 2 neutron stars, the compressed remnants of massive suns that had exploded millions of years before, had finally collided after spiraling toward each other for an eternity. The collision lasted milliseconds. In those milliseconds, a volume of matter smaller than a city but heavier than our sun was compressed, twisted, and torn apart with such ferocity that the surrounding space itself shook. Gamma rays burst outward. A bloom of glowing debris expanded at a substantial fraction of the speed of light. Scientists watching from observatories around the planet and from instruments in Earth orbit saw it all unfold in real time, 130 million light-years away. And buried in the spectral data of that glowing cloud was a signature, a chemical fingerprint. The unmistakable signature of freshly minted heavy elements, including gold, platinum, and uranium, being forged in real time. This was the first time humanity had ever watched an element being born. Think about what that means. You have held objects made of gold. You may be wearing one right now. That gold did not come from a star that peacefully burned out. It did not form in a supernova. It was hammered into existence during an event so violent that the surrounding space literally warped and buckled. Every gram of gold on this planet arrived here carrying the memory of a collision like the one we witnessed in 2017. And uranium, which is heavier than gold, required the same forge. The process is called the R process, short for rapid neutron capture. In the crushing environment of a neutron-star merger, atomic nuclei are bombarded by free neutrons so quickly that they cannot decay before capturing another and another and another. In fractions of a second, iron nuclei grow heavier and heavier, climbing the periodic table rung by rung, becoming elements that no quiet star could ever produce. By the time the cloud cools and disperses, it carries within it the seeds of almost every heavy element in existence. And this process does not happen often. For context, a neutron-star merger of sufficient energy to produce meaningful quantities of uranium is estimated to occur perhaps once every 10,000 to 100,000 years in a galaxy the size of the Milky Way. These events are cosmically rare, which means that the uranium in the Earth's crust is not the product of hundreds of stellar generations building up quietly over time. It is the legacy of a small number of catastrophic moments scattered across the history of our galaxy, each one leaving behind a cloud of heavy elements that eventually mixed into the gas and dust of interstellar space. Several billion years ago, one of those clouds contributed its material to the nebula that would become our solar system. Gravity pulled the gas and dust inward. The center grew hot and ignited as the sun. The remaining material flattened into a disk, clumped, collided, and over tens of millions of years assembled itself into planets. And the young Earth, still molten and chaotic, received its share of that ancient stellar violence in the form of heavy elements locked into its rock. Uranium did not arrive on Earth as a gift. It arrived as shrapnel. And for 4.5 billion years, it has been sitting in the crust, slowly, inexorably decaying. But here's the thing about that decay, the thing that almost nobody realizes, the thing that will change how you think about the ground beneath your feet. That slow, steady disintegration is not just a curiosity. It is not just a physicist's footnote. It is the reason this planet is alive. And we are going to get to that. But first, I want you to sit with this for a moment. The element we are talking about, the one that will thread through every chapter of this story, was born in a collision so violent that it bent the geometry of space. It crossed 130 million light-years of void. It waited inside a dying star, then a cloud of gas, then a planetesimal, then the crust of a cooling world. It waded through the formation of the ocean. It waded through the first bacteria, through the first fish, through the first footstep on land. It waded through the dinosaurs. It waded through the ice ages. It waded through the rise of every civilization you have ever read about. And then, in 1789, a German chemist looked at a piece of black mineral and decided to investigate. The waiting was finally over. Let us talk about what it actually means to build an atom heavier than iron. In the periodic table, hydrogen is number 1. Helium is number 2. The numbers go up as you add protons to the nucleus. Iron sits at number 26. For most of cosmic history, stars are extraordinarily good at producing everything up to iron. They fuse hydrogen into helium, helium into carbon, carbon into oxygen and silicon, and so on, climbing the ladder of elements through a series of fusion reactions that release energy and keep the star burning. But iron is different. Fusing iron does not release energy. It absorbs it. For a star, iron is the end of the road. You cannot burn it. You cannot go further up the ladder through ordinary stellar fusion. So how does uranium, element number 92, exist at all? How does nature build something 66 steps heavier than iron? The answer is neutrons. Neutrons have no electric charge. This makes them, in nuclear physics, something like master keys. When a charged particle like a proton tries to approach an atomic nucleus, it has to fight through a powerful electromagnetic repulsion, the Coulomb barrier, which grows stronger the heavier the nucleus becomes. But a neutron slides right past this barrier without resistance. It can walk up to a nucleus and be absorbed without any need to overcome that repulsion. In stars near the end of their lives, 2 slower processes can add neutrons to nuclei over long timescales, and this accounts for many of the elements heavier than iron that we find in the universe. But uranium is so heavy, so far up the periodic table, that these slow processes cannot reach it before the unstable intermediate nuclei decay away. To build uranium, you need to add neutrons faster than those nuclei can decay. Much faster. Hundreds of times faster. That is the R process, rapid neutron capture. And the only place in the observable universe where conditions are extreme enough to drive the R process is the collision of 2 neutron stars, or possibly certain hypernovae, the collapse of the most massive stars. In either case, we are talking about events that push matter to densities and temperatures that simply do not exist anywhere else. Densities at which a teaspoon of material would weigh hundreds of millions of tons, temperatures measured in hundreds of billions of degrees. In those conditions, a nucleus can capture 10, 20, 30 neutrons in a fraction of a second. It climbs the ladder of mass so quickly that by the time the environment cools and the neutron flood subsides, it has reached configurations so heavy and unstable that they will eventually decay, step by step, back down to something more stable. And after that cascade of radioactive decays, what remains includes uranium-238 and uranium-235, the two isotopes that will become central to everything that follows in our story. Now consider the journey from that point of origin to the present moment. A neutron-star merger occurs. It takes place somewhere in the Milky Way, perhaps 4 or 5 billion years before our solar system forms. The expanding debris cloud cools over millions of years. The heavy elements within it, including freshly minted uranium, mix with the surrounding interstellar medium, slowly spreading through space as the cloud is stirred by stellar winds and the slow gravitational currents of the galaxy. Generations of stars are born and die in the surrounding region, adding their own processed material to the mix. And over hundreds of millions of years, a particular region of the galaxy gradually accumulates the ingredients for a new solar system. Then, roughly 4.5 billion years ago, a trigger, perhaps the shock wave from a nearby supernova, or simply the slow accumulation of mass in a dense molecular cloud, causes a region to collapse. Gas falls inward. Dust spirals with it. The center heats up and ignites as the proto-sun. A disk of material orbits it, and in that disk, particles collide and stick, growing from dust grains to pebbles to boulders to planetesimals, and eventually to planets. One of those planets forms at just the right distance from the sun to allow liquid water. It is struck repeatedly by smaller bodies carrying volatiles, water, carbon compounds, and heavier elements. Its surface is initially a magma ocean, entirely molten, catastrophically hot. Heavy elements including iron and nickel sink toward the center. Lighter silicates float toward the surface. And uranium, with its preference for certain mineral structures, concentrates in the lower crust and upper mantle, scattered through the rock at concentrations of a few parts per million. Not a dramatic abundance, not a vein or a seam of pure metal. Just a faint, even dusting of radioactive atoms, distributed through billions of cubic kilometers of rock. But here's the question you should be asking right now. Why does any of this matter? Why is it significant that uranium ended up dispersed through the Earth's crust? The answer is that uranium is not stable. It never has been. Every single atom of uranium-238 that formed in that ancient neutron-star merger is slowly, inexorably decaying. It has been decaying since it formed. It decayed while it drifted through space. It decayed while it was incorporated into the early Earth. It has been decaying for 4.5 billion years, and it will continue to decay for billions more. The period at which half of any given sample decays is called the half-life. For uranium-238, that figure is 4.468 billion years, which is almost exactly the current age of the Earth. For uranium-235, it is 703 million years. These are the clocks built into the rock of this planet. They cannot be sped up. They cannot be slowed down. They tick at exactly the same rate regardless of temperature, pressure, chemistry, or anything else. They are perhaps the most reliable timekeepers in the universe. But before we get to what that means for human knowledge, we need to stay with the physical reality of all that decay. Because the decay of uranium is not just a passive curiosity, it is an engine. And that engine has been running the planet we live on for as long as the planet has existed. Let me give you a sense of scale. If you took all the uranium-238 that has decayed inside the Earth over the past 4.5 billion years, the energy released would be almost incomprehensible by any human standard. Each individual decay event releases a small amount of energy, mostly in the form of heat. But multiply a small amount by trillions of trillions of trillions of events happening continuously over geological time, and you get a contribution to the Earth's interior heat budget that rivals the residual warmth from the planet's own formation. That is the setup for what comes next. Let me destroy a myth. You probably learned at some point that the Earth is hot inside because it formed hot. The collision of planetesimals, the kinetic energy of all that falling material, generated enormous heat during the planet's formation, and the Earth has been slowly radiating that heat away ever since. This is true. It is part of the story, but it is not the whole story, and the missing piece changes everything. Here is the problem. Models of planetary cooling showed that if the Earth were losing heat only through the gradual radiation of its primordial warmth, it should be significantly cooler by now than it actually is. The numbers do not add up. Something has been supplying additional heat to the planet's interior for billions of years. Something has been keeping the fire going long past the point when it should have dimmed. That something is radioactive decay. Uranium, thorium, and potassium-40, distributed through the Earth's mantle and crust, have been releasing heat continuously through their radioactive decay for the entire lifetime of this planet. Current estimates suggest that between 40 and 50% of the Earth's total heat flux, the heat flowing outward from the interior, comes from radioactive decay. The exact figure is still debated among geoscientists, and measuring it precisely requires instruments at the bottom of the ocean and detectors sensitive to the ghostly particles called antineutrinos that radioactive decay produces. But the broad picture is clear. Close to half of this planet's internal heat engine runs on nuclear fuel. Think about what that means. Right now, under the ground where you are standing, uranium atoms are splitting. Their decay products slam into surrounding minerals, converting their kinetic energy into heat. That heat rises slowly through the mantle by convection, the same process that moves heat in a pot of water on a stove, except that the stove has been on for 4.5 billion years, and the pot is the size of a planet. Now consider what that convection does. The mantle, despite being made of solid rock on human timescales, flows on geological timescales like an incredibly viscous fluid. Hot material rises toward the surface. Cooler material near the surface sinks. This enormous, slow churning drives the movement of tectonic plates. The continents you live on are riding atop convection cells in the mantle, powered, in significant part, by the radioactive decay of uranium and its siblings. Every earthquake, every volcanic eruption, every mountain range thrust upward by colliding plates, every ocean basin opening as continents drift apart. All of this is downstream of nuclear energy. But there is something even more important than plate tectonics. The mantle convection also stirs the liquid outer core of the Earth, where molten iron generates the planet's magnetic field. This field, called the geodynamo, extends far above the atmosphere and deflects the solar wind, the constant stream of charged particles pouring off the sun. Without the magnetic field, the solar wind would strip away the Earth's atmosphere over geological timescales, just as it stripped away the atmosphere of Mars billions of years ago when Mars's core cooled and its dynamo shut down. Mars has a thin, cold, almost airless surface. Earth has oceans, weather, and life. One significant reason for that difference is that Earth retained its internal heat long enough for the geodynamo to persist, protecting the atmosphere through billions of years of evolution. And a significant contributor to that retained heat is uranium. Let me say this as plainly as possible. Without radioactive uranium in the Earth's crust and mantle, the planet would have cooled faster. The mantle would have become more sluggish. Plate tectonics might have slowed or stopped. The core's convection would have weakened. The magnetic field would have diminished. The atmosphere would have been gradually eroded by the solar wind. The oceans would have evaporated into space. And complex life as we know it would not have had a stable enough environment to evolve. This is not a small claim. This is one of the foundational arguments for why Earth is Earth and not another dead rock. And at the center of it is a radioactive element that most people only think about in the context of bombs and power plants. The element that humanity's popular imagination associates primarily with destruction is, in geological reality, one of the central reasons life was able to exist on this planet at all. Uranium kept the lights on, in a very literal sense, long before we knew it existed. Here is a perspective that I want you to carry forward into the rest of this story. We tend to think of radioactivity as something unnatural, something dangerous that was unleashed by human technology and that does not belong in the natural world. But radioactivity is not a human invention. It is a fundamental property of the universe. The Earth itself is radioactive. It always has been. The radioactive decay of uranium and its companion elements is not a contamination of nature. It is one of nature's engines. It is part of what makes this planet hospitable. The story of uranium is, in part, the story of humanity learning that the universe was more powerful and more complex than we imagined, and then spending the next century trying to decide what to do with that knowledge. We walk on a planet warmed by nuclear fire. We breathe air protected by a magnetic shield powered, in part, by atoms falling apart. We live on continental landmasses that are being moved, slowly but continuously, by heat that comes partly from radioactive decay. This has been true for the entire history of life on Earth. It will be true long after everything that currently exists in human civilization is dust. The irony, the profound, disorienting irony, is that uranium was protecting life long before any living creature was capable of fearing it. And here is one more layer to add, one more dimension to this picture that I think is worth sitting with for a moment. The heat generated by radioactive decay in the Earth's interior is not constant. It is slowly diminishing. Uranium-238 has a half-life of 4.468 billion years, which means that over time, less and less of it remains, and the heat it generates decreases proportionally. The same is true of uranium-235 and thorium. Billions of years from now, the Earth's radioactive fuel will be largely spent. The mantle will cool. The convection will slow. Plate tectonics will eventually cease. The core will solidify. The geodynamo will shut down. The magnetic field will collapse. And without that field, the solar wind will begin to erode the atmosphere, slowly but inexorably, over hundreds of millions of years. The Earth is not a permanent habitat. It is a temporary one. And the clock that is running down, the timer that ultimately determines how long this planet can remain alive in the way we know it, is set by the half-life of radioactive elements, uranium chief among them. We are living in the middle of the story, not at its beginning and not near its end, but somewhere in an extraordinarily fortunate window of time when the planet's nuclear fuel is abundant enough to keep the fires burning and the magnetic shield in place. That window has been open for 4.5 billion years. It will remain open for billions more. But it is a window, not a permanent door. And uranium's slow decay is both the reason the window is open now and the reason it will eventually close. This is the planet we live on. Not a passive, static background for human events, but an active, evolving system powered by nuclear chemistry happening constantly in the rock beneath us. When you feel an earthquake, you are feeling the distant consequence of uranium decay. When a volcano erupts, it is expelling material mobilized by mantle convection, driven partly by radioactive heat. When a compass needle points north, it is responding to a magnetic field maintained by a dynamo running on heat that uranium helped supply. None of this requires you to think differently about anything practical. You do not need to change your daily life based on the knowledge that the Earth's interior runs on nuclear energy. But I think it genuinely matters, in a way that is hard to articulate precisely, to understand the ground you stand on more fully. The planet that hosts all of human history, all of human civilization, all of human meaning, is itself a nuclear machine. And uranium is one of its key components. Now we pull back from the planetary scale and zoom into something much more intimate. A man, a hammer, a dark mineral, and a moment of curiosity that would change the world in ways nobody involved could possibly have imagined. We are in the Erzgebirge, the Ore Mountains, straddling what is now the border between Germany and the Czech Republic. The year is the late 1700s, and for centuries this region has been one of the great mining heartlands of Central Europe. Silver, tin, cobalt, bismuth, the mountains have given up their treasures to generations of miners who hacked at the rock with iron tools and carried their loads to the surface in baskets and carts. These are men who knew the minerals of these mountains the way a farmer knows his soil, by sight, by weight, by smell, by the feel of them against a pick. And they knew one mineral in particular that they hated, a heavy, black, greasy substance that sometimes appeared in the tunnels alongside the silver ore they were actually looking for. It looked promising, the way only things that disappoint you can look promising. It had a certain density, a certain heft, a certain shine in the lamplight, but it contained no silver worth recovering. It yielded nothing profitable, and so the miners gave it a name that perfectly expressed their contempt. They called it pechblende, pitch blende. Pitch because of its dark, resinous appearance. Blende, a German mining term for a mineral that deceives, that looks valuable but tricks you into wasting your effort on it. They threw it in the waste pile. Generation after generation of miners hauled this heavy, worthless rock out of their tunnels and discarded it in growing heaps outside the mine entrances. It sat there in the mountain air, unremarked and unloved, while the silver trade built the economies of the surrounding towns. Nobody suspected that the waste pile was, in fact, the most extraordinary material in the known world. In 1789, a Berlin chemist named Martin Heinrich Klaproth received a sample of pechblende and began to analyze it. Klaproth was one of the great analytical chemists of his era, a meticulous and talented investigator who had already made significant contributions to the identification of several elements. He dissolved the mineral in acid, subjected it to a series of chemical treatments, and isolated something he had not seen before. A yellow powder with properties that did not match any known element. Klaproth was reasonably certain he was looking at a new metal, though what he had actually isolated was an oxide rather than pure metallic uranium. But the discovery was real. A new element had been found in the waste heaps of the ore mountains. He named it uranium. The name was a deliberate reference to the planet Uranus, which had been discovered just 8 years earlier by William Herschel and was causing considerable excitement in the scientific community. Naming new discoveries after newly found celestial bodies was very much in fashion. It was a gesture that tied earthly chemistry to the grandeur of the heavens. It was also, as history would reveal, more appropriate than Klaproth could possibly have known. But here is where the story takes a turn towards something much closer to home than planetary geology or cosmic history. Because uranium's first entry into everyday human culture had nothing to do with energy, nothing to do with weapons, and nothing to do with any of the great scientific dramas that would follow. Its first appearance in ordinary life was decorative. Uranium compounds, when added to glass during manufacturing, produce a vivid, warm, fluorescent glow. In sunlight, uranium glass appears a rich amber or pale yellow-green. But under ultraviolet light, the same glass blazes with an intense, almost supernatural green luminescence that looks like nothing else in the natural world. Throughout the 19th century, from roughly the 1830s through the early 1900s, uranium glass was manufactured across Europe and North America in enormous quantities. Bowls, vases, drinking glasses, plates, figurines, lampshades, decorative tiles, beads for jewelry. The color was fashionable, distinctive, and beautiful in a way that clear glass simply could not match. And if you think about this from the perspective of a middle-class family in the 1880s or 1890s, uranium glass was simply a lovely, moderately expensive household product. It sat on shelves. It was used at dinner parties. It was given as gifts. Children drank from uranium glass cups. Grandmothers kept uranium glass vases with flowers on the windowsill. The material was treated with the casual familiarity of any pleasant domestic object. Nobody told them it was radioactive. Nobody told them it was constantly emitting ionizing radiation in all directions. The word radioactive did not exist. The concept of radioactive decay had not been formulated. The very idea that matter could spontaneously shed energy through some internal, invisible process was not part of any scientific framework yet. It would not be for another decade after the first uranium glass was manufactured. So there is this strange, quietly unsettling historical reality. For 60 or 70 years, across Europe and America, people were living with mildly radioactive objects in their homes, using them as tableware, holding them in their hands, keeping them close to their faces. The radiation doses involved were low, nothing like what would later come with industrial uranium processing, but the ignorance was total and absolute. Now, I want to pause here and address something. Because today, when you hear about uranium glass, there's sometimes a tendency in popular media toward a kind of exaggerated horror, as if everyone who ever owned a piece was walking toward an inevitable early death. This is not accurate. The concentrations of uranium used in decorative glass were modest, and the radiation doses from normal household use were small. Uranium glass collectors still exist today, and while common sense precautions like not eating off it regularly are sensible, The historical glass objects in antique shops are not radiological emergencies. The risk was real, but subtle. Prolonged, sustained exposure to any source of ionizing radiation increases certain health risks marginally. But the 19th century uranium glass trade was not a mass poisoning event. What it was a perfect symbol of the central irony that runs through the entire human history of uranium. We encounter this element long before we understand it. We use it, live with it, build with it, shape it into objects of beauty or utility without any awareness of its deeper nature. The ignorance is not malicious. It is simply the condition of being early in the story. The families who displayed uranium glass vases on their mantelpieces were not fools. They were simply people who did not yet have the knowledge that would eventually change everything. The same ignorance that let them drink from uranium cups without fear would, in a slightly different form, persist into the laboratories where scientists studied the element itself. Knowledge arrived slowly, and it arrived at a cost. The next chapter in the story of uranium would begin in Paris in the 1890s with a physicist who decided to investigate some unusual rays that another scientist had almost accidentally discovered and thought unimportant. She would spend the rest of her life following that thread into the heart of the atom, and the thread would eventually kill her. But first, the discovery, and the accident that made it possible, and the overcast sky over Paris in February of 1896, that, because it blocked the sunlight one particular scientist needed for his planned experiment, set in motion a chain of events that would lead to everything that came after. Sometimes the weather changes history. Paris, February of 1896, and the sky over the city has been gray and overcast for days. Henri Becquerel, a physicist at the Museum of Natural History, is preparing an experiment about phosphorescence, the phenomenon by which certain materials absorb sunlight and then re-emit it as a gentle glow after the light source is removed. His hypothesis is straightforward. Phosphorescent materials must first be energized by sunlight before they can release their stored glow, and uranium salts are famously phosphorescent. His plan is to expose crystals of potassium uranyl sulfate to bright sunlight, then place them on a photographic plate wrapped in black paper to see if their emitted glow could penetrate the wrapping and expose the film. But the sun refuses to cooperate. Paris stays cloudy. Day after day, Becquerel prepares his setup, the uranium crystals resting on the wrapped photographic plates in his drawer, and day after day, the sun stays hidden. He is about to set the whole experiment aside when, out of a mixture of professional habit and mild curiosity, he develops the photographic plates anyway, expecting to find them blank, or nearly blank, since the uranium crystals had never received the sunlight he assumed they needed. What he finds instead stops him cold. The plates are not blank. They are darkened, exposed, as thoroughly as if they had been held under a bright light for hours. The uranium crystals, sitting in complete darkness inside a closed wooden drawer, have somehow passed invisible rays through the black paper wrapping and exposed the photographic emulsion beneath. Something is coming out of the uranium. Not reflected light. Not stored sunlight. Something entirely different. Something that the uranium is generating on its own, from inside itself, without any external energy source whatsoever. Becquerel publishes his results, announces that uranium emits rays spontaneously, and then, almost inexplicably, the scientific community largely shrugs. The finding is curious, yes, but nobody quite knows what to make of it. It does not fit into any existing framework. It does not suggest an obvious application. And so the discovery that should have electrified physics quietly sits in the journals for a year or two, waiting for someone with the drive and the intuition to pick up the thread and follow it wherever it leads. That someone is a 29-year-old Polish student living in a cold rented attic room in the Latin Quarter of Paris, surviving on bread and chocolate, studying mathematics and physics at the Sorbonne with an intensity that her professors found almost unsettling. Her name is Maria Sklodowska, and she will become the most celebrated scientist in history under the name Marie Curie. But at the moment, she is simply a foreign student looking for a research topic for her doctoral dissertation. And when she reads Becquerel's overlooked paper about the spontaneous rays from uranium, something about it strikes her as exactly the kind of problem she wants to spend her life on. The other students and researchers are pursuing well-defined questions with established methodologies. Marie chooses the abandoned mystery. She borrows a laboratory and a piece of equipment, a sensitive electrometer developed partly by her husband, Pierre Curie, and she begins measuring the electrical conductivity of air near uranium samples. The invisible rays, she finds, ionize the air, making it conduct electricity, and the strength of that ionization is directly proportional to the amount of uranium present. The effect, she concludes, is an intrinsic property of the uranium atom itself. It does not depend on the mineral the uranium is in. It does not depend on the chemical form. It does not depend on the temperature or the light level or any external condition. It is something the atom does spontaneously, continuously, and independently. She coins a word for this property: radioactivity. Radioactivity. And then she makes a second observation, one that is even more important than her first. She tests the radioactivity of pitchblende, the same heavy black mineral the Ore Mountains miners had been throwing away for centuries, and she discovers that pitchblende is significantly more radioactive than pure uranium metal, more radioactive than the uranium it contains. The mathematics is unambiguous. There must be something else in the pitchblende, something far more intensely radioactive than uranium, that is boosting the overall radiation of the mineral. Something unknown. Something not yet in any chemist's inventory of elements. Together with Pierre, who has abandoned his own research to join the hunt, Marie sets out to find it. The process is one of the most physically brutal in the history of science. They work in a leaky shed in the courtyard of the School of Physics, the shed so damp and cold in winter that solutions freeze in their equipment. They are processing ton after ton of pitchblende residue, the same waste material the miners discarded, dissolving it in acid, precipitating it, filtering it, crystallizing it, evaporating it, repeating the process hundreds of times to isolate the radioactive component, which is present in concentrations so minute that tons of ore yield only fractions of a gram. Marie's hands are perpetually burned and cracked from the acid. Both she and Pierre suffer from chronic fatigue and illness that they attribute to overwork. They have no idea that the material they are handling every day is irradiating them continuously, damaging their cells, accumulating damage in their bone marrow that will eventually prove fatal. In 1898, they announced the discovery of two new elements. The first they name polonium, after Marie's homeland, Poland, which at the time did not exist as an independent nation on any map. The second they name radium, from the Latin word for ray, because its radioactivity is millions of times more intense than uranium's. The scientific world is stunned. In 1903, Marie and Pierre received the Nobel Prize in Physics, shared with Becquerel. Marie is the first woman to receive a Nobel Prize. Then, in 1906, Pierre is killed in a street accident in Paris, his skull crushed under the wheels of a horse-drawn cart in the rain. Marie is 48 years old and suddenly a widow with two daughters, and she does something that nobody in the history of the Nobel Committee had anticipated. She goes back to the laboratory. She continues alone. She continues with a ferocity and focus that leaves people around her in silent awe. In 1911, she receives a second Nobel Prize, this time in chemistry, for the isolation of pure radium metal. She remains to this day the only person who has ever received Nobel Prizes in two different scientific disciplines. She runs military radiography units during the First World War, bringing mobile X-ray equipment to field hospitals. She establishes the Radium Institute in Paris. She trains generations of scientists, and through all of it, for decades of continuous exposure, she works with radioactive materials using no protective equipment beyond a thin laboratory coat, because the danger is not understood, not by her, not by anyone. The connection between ionizing radiation and cellular damage is being assembled, slowly, from a growing body of troubling evidence. The strange skin lesions that appear on researchers, the anemia, the fatigue that never quite resolves. But the full picture does not arrive in time for Marie. She dies in 1934 from aplastic anemia, her bone marrow destroyed by a lifetime of radiation exposure. She is 66 years old. Her daughter Irene, who also worked in radioactive research, will die of leukemia 22 years later. And here's a detail that makes the reality of Marie Curie's legacy almost physically present. Her personal notebooks from the 1890s, the ones in which she recorded her earliest measurements and calculations, are still radioactive today. They are stored in lead-lined boxes at the Bibliothèque Nationale de France in Paris. Any researcher who wishes to examine them must sign a formal waiver acknowledging the radiation risk and must handle the pages wearing protective gear. 130 years after Marie Curie sat in that cold shed and bent over those pages, the radioactive contamination she left on them persists, detectable, measurable, real. The woman who gave us the word radioactivity left behind documents that physically demonstrate the concept to this day. Her notebooks are both a scientific record and a monument, and the monument is made of the same thing that killed her. In 1932, a British physicist named James Chadwick discovered a particle that had been theorized for over a decade, but never directly observed: the neutron. We have already spoken about neutrons in the context of stellar nucleosynthesis, about how they can slip past the electromagnetic defenses of an atomic nucleus without resistance. But in 1932, the neutron was not a concept from astrophysics. It was a fresh experimental result, a new tool sitting in the hands of physicists who were beginning to understand that the nucleus of an atom was not a simple static object, but a complex dynamic structure that could be probed, altered, and potentially destabilized. Within 2 years, the Italian physicist Enrico Fermi had an idea so simple and so systematic that it had the character of genius. He would take every element in the periodic table, in order, and bombard each one with neutrons and see what happened. He worked through the table methodically, from hydrogen upward, and in most cases the result was a heavier isotope of the same element, the nucleus having absorbed a neutron and gained 1 unit of mass. When he reached uranium, element 92, the heaviest known element, something strange occurred. The bombardment products did not match any known element. Fermi and his colleagues analyzed the chemistry and concluded, reasonably but incorrectly, that they must have created new elements heavier than uranium, so-called transuranic elements that had never existed in nature. This was announced, celebrated, and accepted by much of the scientific community. But a small number of chemists were troubled. The results did not quite fit. One of them was a German radiochemist named Ida Nodak, who in 1934 published a paper suggesting an alternative interpretation. Perhaps the uranium nucleus was not gaining neutrons and becoming heavier, but was instead splitting into 2 pieces, producing known lighter elements. The scientific community essentially ignored her. The idea was considered too radical, too far outside the existing theoretical framework to be taken seriously. And so the correct answer sat in the published literature for 4 more years, unread and disregarded, while Fermi's incorrect interpretation remained dominant. Then, in December of 1938, in Berlin, Otto Hahn and Fritz Strassmann performed the definitive experiment. They bombarded uranium with neutrons and carefully analyzed every product, and they found barium. Barium is element 56. It is roughly half the atomic weight of uranium. If barium was appearing in the reaction products, the uranium nucleus was not growing larger. It was splitting in half. Hahn was a chemist, meticulous and careful, and he wrote immediately to Lisa Meitner, his longtime scientific collaborator, who had been forced to flee Germany earlier that year because she was Jewish, and who was now in Stockholm working at the Nobel Institute. The letter reached her over the Christmas holiday of 1938, while she was staying with relatives in the Swedish coastal town of Kungälv. Her nephew, the physicist Otto Frisch, was visiting her, and on the morning after the letter arrived, they went for a walk in the snow, Meitner on foot and Frisch on cross-country skis, and on that walk they worked out the physics of what Hahn had found. The uranium nucleus, Meitner explained, was not like a hard solid ball. Nuclear theory, specifically the liquid drop model developed partly by Niels Bohr, suggested it behaved more like a liquid drop, held together by the strong nuclear force, but slightly deformable. When a neutron struck it and was absorbed, the drop began to oscillate, stretching and vibrating. If the neutron added enough energy, the elongated drop could pinch off into 2 smaller droplets, 2 entirely new atomic nuclei, with a combined mass slightly less than the original uranium nucleus. And that missing mass, the small difference between the mass of the uranium nucleus plus neutron before the event and the combined mass of the 2 product nuclei after it, was converted directly into energy according to the equation that Albert Einstein had published 33 years earlier. E equals mc squared. The speed of light is approximately 300 million meters per second. Squared, that number is 9 times 10 to the 16th power. Even a tiny missing mass, multiplied by that factor, produces an enormous amount of energy. Frisch did the calculations standing in the snow in Sweden, and the result was staggering. A single uranium fission event released about 200 million electron volts of energy. A typical chemical reaction releases a few electron volts. Nuclear fission released roughly 100 million times more energy per reaction than any chemical process. Frisch rushed back to Copenhagen and confirmed the result experimentally within days. Meitner and Frisch published their theoretical explanation. Frisch borrowed a term from biology to name the process: fission, the division of a cell into two. Within weeks, physicists across Europe and America had reproduced the result. The physics was simple, reproducible, and terrifying. Because there was an additional feature that nobody had yet fully processed, but that would become the most consequential physical fact of the 20th century. Each uranium fission event released not just energy, but also additional free neutrons, typically 2 or 3. And those free neutrons could strike other uranium nuclei and cause them to fission in turn, which would release more neutrons, which would cause more fissions. A chain reaction. Self-sustaining, exponentially multiplying. And over Europe, the spring of 1939 was already shadowed by the certainty of war. Nazi Germany had annexed Austria and Czechoslovakia. The scientists who had fled to America, Hungary-born Leo Szilard, German-born Albert Einstein, Italian-born Enrico Fermi, understood something that politicians and generals had not yet grasped. The same physics that had just been demonstrated in a Berlin laboratory could, in principle, be used to build a weapon of incomprehensible destructive power. Szilard, who had actually conceived of the idea of a nuclear chain reaction in the early 1930s as a thought experiment and had attempted to patent it to prevent its military misuse, was nearly frantic with urgency. He tracked down Einstein at his summer house on Long Island in New York and explained the situation. Einstein, who had been largely removed from nuclear research for years, grasped the implications immediately. Together with Szilard and physicist Edward Teller, they drafted a letter addressed to President Franklin D. Roosevelt. The letter explained, in measured but direct language, that recent research had demonstrated the possibility of setting up nuclear chain reactions in uranium, that this process could be used to construct extremely powerful bombs, that Germany had already stopped the sale of uranium from the Czech mines it had seized, suggesting awareness of uranium's strategic value, and that the United States should take immediate action to acquire uranium supplies and accelerate its own research. Einstein signed the letter in the summer of 1939. It was delivered to Roosevelt in October of that year, 2 months after Germany invaded Poland and the Second World War began. The president's initial response was cautious. He authorized a modest advisory committee, the Uranium Committee, and allocated its first budget, $6,000. The most consequential scientific program in human history began, at its very inception, with a budget smaller than many kitchen renovations. The machine was starting, slowly at first, and then with a speed and scale that would transform the world. There is a factory in Tennessee that most people have never heard of, and it is one of the most extraordinary structures ever built. The K-25 gaseous diffusion plant in Oak Ridge was constructed in the early 1940s as part of an effort so secret that the workers building it had no idea what it was for. The managers in one section did not know what was happening in the next section, and even the state of Tennessee had not been told that a facility the size of a small town was being quietly assembled in the valley below Clinch Mountain. When it was completed in 1945, K-25 was the largest building under a single roof in the world, 1/2 mile long, 1/4 mile wide, 5 stories tall. And inside, it ran a continuous cascade of thousands of porous barriers through which gaseous uranium hexafluoride was pumped. The slightly lighter molecules containing uranium-235 drifting fractionally faster than the slightly heavier molecules containing uranium-238. Each passed through a barrier enriching the mixture by a fraction of a percent. and after thousands of such passes, the concentration of uranium-235 grew from its natural level of just over 0.7% to the 90% plus level required for a weapon. The scale of the enterprise that produced the first nuclear weapons has no precedent in the history of science or engineering. At its peak, the Manhattan Project employed over 130,000 people across dozens of sites in the United States, Canada, and the United Kingdom. It consumed resources equivalent to the entire United States automobile industry. It was funded at a level of approximately $2 billion, roughly equivalent to $30 billion in today's terms, authorized through a secret appropriations process that bypassed normal congressional oversight. The scientists at the center of it included some of the greatest minds of the 20th century, working under conditions of extraordinary secrecy, isolated in purpose-built communities, forbidden from discussing their work with family members, some of whom genuinely did not know what their spouses or parents were doing for years. The intellectual heart of the project was Los Alamos, New Mexico, a laboratory assembled in the desert on the mesa above the Rio Grande, where Robert Oppenheimer, a theoretical physicist from Berkeley, gathered physicists, mathematicians, chemists, and engineers from across the Western world, many of them European refugees from fascism, to work on the specific problem of designing and building a functional atomic weapon. And throughout all of this, uranium was the thread. Uranium ore, mined in the Belgian Congo and shipped across the Atlantic. Uranium metal, processed in Chicago. Uranium hexafluoride, pumped through the vast cascades in Oak Ridge. Uranium-235, painstakingly concentrated from tons of natural uranium until there was enough to assemble a critical mass. By 1945, the scientific problem was largely solved. The engineering challenges had been overcome. The weapon existed in two versions: a gun-type design using uranium-235 and an implosion design using plutonium, itself produced from uranium-238 in the reactors at Hanford, Washington. The test of the plutonium design, codenamed Trinity, took place at 5:30 in the morning on July 16, 1945, in the Jornada del Muerto Desert in New Mexico. The device was placed atop a 100-foot steel tower. In the pre-dawn darkness, a network of cables and switches waited for the signal. At the moment of detonation, a flash of light more intense than the midday sun illuminated the desert for miles in every direction. A blast wave rolled outward, flattening scrub brush. A column of superheated air and debris rose into the sky, forming the shape that would become the most recognizable symbol of the atomic age. The sand beneath the tower was fused by the heat into a glassy greenish substance, later named trinitite, that remained mildly radioactive for decades. Oppenheimer, watching from the observation post, recalled lines from the Hindu scripture, the Bhagavad Gita. "Now I am become death, the destroyer of worlds." 3 weeks later, a uranium-235 bomb called Little Boy was loaded into a B-29 bomber named Enola Gay and dropped over the city of Hiroshima, Japan, on the morning of August 6th. The device contained approximately 64 kilograms of enriched uranium. Of that total, less than 1 kilogram actually underwent fission in the explosion. The energy released by less than 1 kilogram of uranium fission, in fractions of a second, destroyed approximately 60% of the city and killed somewhere between 70,000 and 80,000 people immediately, with the total death toll over the following months and years estimated at somewhere between 90,000 and 166,000, a range reflecting the difficulty of counting the dead in a city that had ceased to function. 3 days later, a plutonium bomb destroyed Nagasaki. Japan announced its surrender on August 15th. The war was over. And the world that existed after those 2 mornings in August was permanently, irrevocably different from the world that had existed before them. The element that had spent 4.5 billion years quietly warming the planet from below, that had been discarded in mine waste heaps and shaped into decorative glassware, and observed emitting mysterious rays in a Paris laboratory, had, in the space of a few seconds, demonstrated a capacity for destruction that no human technology had previously approached. The scientists who built it knew, and many of them felt the weight of that knowledge with an almost physical heaviness. In the months and years that followed, Oppenheimer, Szilard, Franck, and others would write, petition, and speak publicly about the moral dimensions of what they had created. Some would devote the rest of their lives to arms control and nuclear disarmament. Others would retreat into silence. The element itself, of course, was indifferent. It did not choose the role it was given. It was doing exactly what it had always done, following the laws of physics, releasing the energy locked inside its nucleus, behaving according to rules written into the fabric of the universe long before there was anyone to fear the consequences. The date is December 20th, 1951, and the location is a stretch of flat, dry land in the eastern Idaho desert that seems, at first glance, to have no reason to be the site of anything important. The experimental Breeder Reactor 1, a machine roughly the size of a large house, has been running carefully calibrated tests for several months under the supervision of physicists from the Argonne National Laboratory. On this particular evening, the operators make a small adjustment to the reactor's control settings, and a turbine begins to spin. And that spinning turbine drives a generator, and that generator produces electricity, and that electricity travels through wires to 4 ordinary incandescent light bulbs that have been mounted on a board specifically for this occasion. And the 4 light bulbs illuminate. The scientists in the room begin to applaud. It is not the most dramatic moment in the history of physics, nothing like the blinding flash in the New Mexico desert 6 years earlier, but it may be the most important in a different sense. Because what happened in that Idaho building on that December evening was the first time in the history of the world that electricity was generated by the controlled fission of an atomic nucleus. The same physics that had been used to destroy Hiroshima had just been used to light a room. It was a proof of concept, modest in scale but enormous in implication. Within a few years, the Soviet Union opened the world's first nuclear power station at Obninsk in 1954, feeding electricity into the public grid of a city. The United States followed with the Shippingport Atomic Power Station in Pennsylvania in 1958. Other countries built their own. By the 1970s, nuclear power had become a mainstream industrial technology, operating reactors in dozens of nations, contributing meaningfully to national electricity supplies. The appeal was, on paper, almost irresistible. 1 metric ton of uranium fuel could produce as much electricity as approximately 3 million tons of coal, with no combustion, no carbon dioxide, no sulfur dioxide, no particulate pollution. In an era before climate change was a widely recognized concern, the argument was primarily economic. Uranium was energy-dense beyond anything the fossil fuel industry could match. But the story of nuclear power is not a simple story of triumph, and to tell it as one would be to misrepresent a technology that has always carried within it both extraordinary promise and genuine difficult risks. The first major warning came on March 28, 1979, at the 3 Mile Island nuclear plant in Pennsylvania, when a combination of equipment failure and human error caused the partial meltdown of the reactor core. The containment structure held. No immediate deaths were directly attributable to radiation. The radiological impact on the surrounding population was later assessed as extremely low. But the psychological and political impact was enormous. The accident demonstrated that nuclear systems could fail in ways that were difficult to predict and control, that the chain of small errors leading to a large outcome was not purely theoretical, and that the public's trust in the industry's safety claims was not something that could be assumed. Then, on April 26, 1986, a reactor at the Chernobyl nuclear power plant in the Soviet Union exploded. The circumstances were specific to the reactor design, a Soviet type called the RBMK, which had a dangerous characteristic called a positive void coefficient. If the coolant water began to boil and form steam bubbles, the reactor would actually become more reactive rather than less, a runaway feedback loop that Western reactor designs had been specifically engineered to avoid. During a safety test conducted under poorly planned conditions in the early morning hours, this feedback loop combined with operator errors and a delayed emergency shutdown to produce an uncontrolled power surge. The reactor vessel ruptured. The graphite moderator caught fire. An explosion blew the roof off the reactor building and sent a plume of radioactive material into the atmosphere that spread across much of Europe. The scale of the accident was unprecedented. Hundreds of thousands of people were evacuated. The firefighters and first responders who arrived in the initial hours, many of them without adequate protective equipment, absorbed radiation doses that would kill a number of them in the weeks and months that followed. The town of Pripyat, home to nearly 50,000 people, was abandoned overnight and has never been re-inhabited. The exclusion zone around the plant remains off-limits to most people today, nearly 40 years later. Then, on March 11, 2011, an earthquake of magnitude 9.0 struck off the coast of Japan, triggering a tsunami that inundated the Fukushima Daiichi nuclear power plant and disabled the cooling systems for 3 reactors. The cores overheated, fuel melted, hydrogen accumulated and exploded, releasing radioactive material into the atmosphere and ocean. The plant was effectively destroyed. Nearly 150,000 people were evacuated from the surrounding region, and large areas remained under evacuation orders for years. These 3 accidents, 3 Mile Island, Chernobyl, and Fukushima, formed the emotional architecture of public perception of nuclear power. They are the 3 moments that define, for most people, what nuclear energy means when it goes wrong. And they are real. The events happened. The harm was real. The disruption of communities, the long-term contamination of land, the anxiety and displacement of hundreds of thousands of people. None of this should be minimized or dismissed. But here is something that the emotional weight of those 3 catastrophes tends to obscure, and I want to present it not as a defense of any particular policy position, but as a factual matter worth knowing. Studies of mortality attributable to different energy sources, conducted by researchers at institutions including Oxford and published in peer-reviewed journals, consistently find that nuclear energy, even accounting for all 3 major accidents and all other incidents combined, has the lowest or one of the lowest rates of deaths per unit of energy produced among all major power sources. Coal, when you include the health effects of air pollution from combustion, kills far more people per unit of energy produced, year after year, through a mechanism that is gradual, statistical, and invisible, and therefore receives almost none of the cultural attention directed at dramatic, visible nuclear accidents. Natural gas produces fewer air pollution deaths than coal, but still vastly more per kilowatt hour than nuclear. Even solar and wind, which produce no direct emissions, carry mortality statistics from industrial accidents during installation and maintenance that, at scale, exceed nuclear's historical record. This is not an argument that nuclear power is safe in some absolute sense, or that the accidents were acceptable, or that every community should welcome a reactor in its backyard. It is an observation about the gap between perceived risk and statistical risk, about how human psychology is far better calibrated to respond to rare, catastrophic, visible events than to slow, chronic, statistically significant ones. Uranium, once again, sits at the center of a profound paradox. The same material whose dramatic failures terrify us most deeply is, in aggregate and over time, far less deadly than the quiet combustion we have been living with for centuries. The question of what we do with that paradox is not a scientific question. It is a question about values, risk tolerance, the distribution of harm across time and space, and what kind of future we are willing to build. And it is a question that uranium has been forcing us to confront, one way or another, since the day the first reactor lit its first light bulb in an Idaho desert on a December evening in 1951. In 1972, a routine quality control check at a uranium enrichment facility in Pierre-Latte, France, produced a result that made the technicians stop and look again. They were analyzing a shipment of uranium ore that had arrived from the Oklo mine in what is now the Republic of Gabon, in equatorial Africa, and something about the isotopic composition of the sample was wrong. Not wrong in a contaminated or corrupted sense, but wrong in a deeply puzzling sense. Uranium, wherever it is found in the world, whether in Australian sandstone or Canadian granite or Kazakh steppe, always contains the same ratio of isotopes. Uranium-238 makes up 99.274% of any natural uranium sample. Uranium-235 makes up 0.72%. These figures are constant across every ore deposit ever analyzed, on every continent and every geological formation, at every depth. The ratio is fixed by the physics of radioactive decay and the age of the solar system, and it does not vary. Except at Oklo it did. The uranium from Oklo was depleted in uranium-235, subtly but unmistakably, in a way that violated the most basic assumptions of isotopic geochemistry. The French Atomic Energy Commission launched an investigation, and what they discovered over the following months is one of the most astonishing findings in the history of Earth science. Approximately 2 billion years ago, in a specific geological formation in what is now Gabon, a naturally occurring nuclear fission chain reaction spontaneously ignited and ran, on and off, for hundreds of thousands of years. Nature had built a nuclear reactor. Without engineers, without control rods, without instrumentation, without any human intention, or even any life form capable of understanding what was happening, the laws of physics had assembled every necessary component in one place and allowed them to interact. The conditions that made it possible were extraordinarily specific. 2 billion years ago, the concentration of uranium-235 in natural uranium was approximately 3%, significantly higher than the 0.7% it is today, because uranium-235 has a shorter half-life than uranium-238 and therefore decays away faster. 3% uranium-235 is enough to sustain a chain reaction, provided the geometry is right and there is a suitable neutron moderator present. At Oklo, the uranium ore had been deposited in a sandstone formation that was saturated with groundwater, and water is an effective neutron moderator. It slows the fast neutrons emitted by fission events down to thermal energies at which they are far more likely to trigger additional fissions. When sufficient uranium-235 had accumulated in the deposit and the groundwater level was right, the chain reaction began. The fissions generated heat. The heat caused the groundwater to boil. When the water turned to steam, the moderation was lost, the reaction slowed and stopped, the rock cooled, groundwater seeped back in, moderation was restored, and the cycle began again. Pulse by pulse, over geological timescales, the Oklo reactor ran its course, processing several tons of uranium-235 and producing a range of fission products including plutonium, cesium, iodine, and dozens of other radioactive isotopes. And then, over the following 2 billion years, the fission products decayed and dispersed. When French scientists analyzed the geology in detail, they found something that transformed Oklo from a scientific curiosity into something with direct relevance to the most pressing practical challenge in contemporary nuclear policy. Almost all of the highly radioactive fission products had remained within a few meters of where they were created. The geological formation, the specific combination of clay minerals, granite, and groundwater chemistry at Oklo had contained and immobilized the waste with extraordinary effectiveness for 2 billion years. 2 billion years. For context, 2 billion years ago, the most complex life on Earth was single-celled organisms. The continents were arranged differently. The oceans had a different chemical composition. Every mountain range that exists today has been razed and eroded away multiple times since Oklo's reactor last ran. And through all of that geological upheaval, the radioactive legacy of nature's nuclear experiment stayed put, held in place by the same rock that had hosted the reactor itself. This matters enormously because the question of what to do with the radioactive waste produced by human nuclear reactors is one of the most technically and politically difficult problems in the entire history of industrial civilization. Every nuclear reactor that has ever operated has produced spent fuel assemblies containing a mixture of highly radioactive isotopes that will remain dangerous for timescales that are genuinely difficult for human minds to process. Some fission products decay to safe levels within decades. Others require centuries. And a handful of the most problematic isotopes, including certain isotopes of plutonium and neptunium, remain significantly radioactive for tens of thousands of years. The entire recorded history of human civilization covers roughly 5,000 years. Written language is about that old. The oldest continuously inhabited cities are about that old. We are being asked to design containment systems for hazardous materials that must remain intact and effective for 20 times longer than the oldest thing our civilization has ever built. As of the early 21st century, the world has accumulated approximately 400,000 metric tons of spent nuclear fuel, stored in cooling pools and dry casks at reactor sites, because no country has yet built and opened a permanent deep geological repository for high-level waste. Many countries have been working on this problem for decades. Sites have been proposed, studied, contested, abandoned, reproposed. The technical challenges are significant. The political challenges are perhaps even larger. Nobody wants a nuclear waste repository in their region, and the waste does not become less radioactive while the political arguments continue. The most advanced response to this problem is a facility being constructed in Finland, in a region of ancient granite bedrock near the town of URANIUM on the coast of the Baltic Sea. It is called onkalo, a Finnish word meaning hiding place or cavity, and it is being bored into granite that has been geologically stable for over 1 billion years, at a depth of approximately 450 meters, far below any groundwater that could carry contamination to the surface. The tunnels of onkalo spiral downward through the rock in a gentle helix, and at the bottom, deposition chambers are being excavated where spent fuel canisters, encased in copper and surrounded by bentonite clay, will eventually be placed and the tunnels backfilled and sealed. The design lifetime is 100,000 years. 100,000 years, 10 times longer than all of written human history. And this requirement for a 100,000-year guarantee generates a problem that has no precedent in human intellectual history, and that has attracted the attention not just of engineers and geologists, but of linguists, anthropologists, semioticians, cognitive scientists, and science fiction writers, because the problem is essentially this. How do you warn people who will exist in 100,000 years not to dig here? The challenge is not physical. The physical containment, buried under 450 meters of billion-year-old granite, is designed to be robust against almost any foreseeable geological event. The challenge is informational. You want to communicate, across an interval of time that dwarfs the entire span of recorded human civilization, a message that conveys danger, the nature of the danger, and the instruction to stay away. But you cannot assume that any language spoken today will still be spoken or readable in 100,000 years. English, Mandarin, French, Finnish, all of the languages in which technical documents about onkalo are currently written are younger than the oldest cave paintings. Language changes beyond recognition over timescales of a few thousand years. In 100,000 years, every language currently spoken on Earth will be as alien to its descendants as Proto-Indo-European is to a modern English speaker. You cannot assume that written script will be legible. The Roman alphabet has been in continuous use for about 2,000 years. 100,000 years from now, it will have the same relationship to the writing system of that era, if any writing system exists, that ancient Sumerian cuneiform has to modern text. You cannot assume that the symbols we associate with radioactive danger, the familiar yellow and black trefoil, will carry any meaning. Symbols lose their referential meaning when the cultural context that defined them is gone. The trefoil is not universally legible even today across all cultures. In 50,000 years, it will be noise. Various proposals have been made. Some researchers have suggested building monuments at the surface, enormous, forbidding structures made of granite and designed to communicate menace and stay away at a purely emotional level. Spike fields, giant stone faces frozen in expressions of distress. Structures that project the feeling of wrongness without requiring linguistic or symbolic interpretation. Others have proposed genetic engineering of plants that would grow in a distinctive, obviously unnatural pattern over the site for as long as the danger persists. A biological warning label that reproduces itself. Others have suggested the deliberate creation of a new tradition, a priesthood or guild of memory keepers who would pass the knowledge of the site's danger from generation to generation as sacred, unchallengeable lore, embedding the warning in religion rather than text. The philosopher François Bastide and the semiotician Paolo Fabri proposed creating a radiation cat, selectively breeding or genetically engineering a line of cats that would change color in the presence of radiation, and then building a global mythology around the idea that a color-changing cat is a warning of invisible danger, embedding it so deeply in folk culture that it persists across civilizational collapse. None of these proposals has been adopted as policy. The problem has no solution that satisfies everyone, or perhaps any solution that satisfies anyone who thinks about it carefully enough. What it has instead is a kind of sublime, vertiginous quality. We have created something that outlasts our ability to communicate about it. We have generated a responsibility that extends beyond the horizon of our imagination. We have left a debt denominated in a currency that future generations may not be able to read, let alone repay. Uranium gave us the energy to run our civilization, and its legacy requires a message written in a language that has not yet been invented, addressed to people who have not yet been born, about a danger they have not yet imagined. The Oklo reactor ran for hundreds of thousands of years and left its waste safely in place. Nature managed the problem without anyone having to write a warning. Whether human civilization can match that record is, at the moment, an open question. Step back for a moment from reactors and repositories and weapons and think about something much smaller and much closer. Think about the air inside your home. Right now, if you are in a house built on certain types of soil or rock, particularly granite-rich or phosphate-rich ground, there is a good chance that a colorless, odorless, tasteless gas is seeping through your foundation and accumulating in your basement or ground floor. You cannot smell it. You cannot taste it. You cannot see it. Your smoke detector will not alert you to it. Your body has no sensation that detects it. It is simply there, invisible, moving through the air you breathe, and if it is present in sufficient concentration and you are exposed to it for long enough, it will significantly increase your lifetime risk of developing lung cancer. The gas is radon, and it is a direct product of uranium decay. Here is how it gets there. Uranium-238, as it decays, does not simply disappear or transform directly into lead. It goes through a series of intermediate steps, a decay chain, passing through more than a dozen different radioactive isotopes before arriving at stable lead-206. One of the steps in that chain is radium-226, and when radium-226 decays, it produces radon-222, a radioactive noble gas. Unlike most of the decay products in the uranium chain, which are solids that stay embedded in whatever mineral matrix they formed in, radon is a gas at ordinary temperatures. It escapes from rock and soil, seeps through cracks in foundations and basement walls, and enters enclosed spaces where it accumulates. Radon itself decays quickly, with a half-life of about 3.8 days, but its decay products are solid and electrically charged, and they attach to airborne particles and to the surfaces of lung tissue when inhaled. It is these short-lived decay products that do the damage, emitting alpha radiation directly into the sensitive cells lining the airways. The World Health Organization estimates that radon is responsible for between 3 and 14% of all lung cancers globally, making it the second leading cause of lung cancer after smoking and the leading cause among non-smokers. In countries with high natural uranium concentrations in the underlying geology, including Finland, Sweden, Norway, parts of the United Kingdom, certain regions of the United States, Canada, and India, indoor radon concentrations can reach levels that represent a meaningful lifetime health risk for occupants. In the United States alone, the Environmental Protection Agency estimates that radon causes approximately 21,000 lung cancer deaths per year. In Finland, where the granite bedrock is particularly rich in uranium and buildings are tightly sealed against the cold, radon has been a recognized public health priority for decades. New buildings are required to incorporate radon mitigation systems. Existing buildings can be tested with simple detectors and equipped with ventilation systems that draw air from under the foundation and vent it outside before it enters the living space. The solutions are not expensive or technically complicated, but they require awareness that the problem exists, and in many parts of the world, that awareness is still absent. Many homeowners have never tested for radon, do not know whether their local geology puts them at elevated risk, and have no idea that their basement might be accumulating a radioactive gas produced by the slow decay of uranium that has been in the ground beneath them for 4 billion years. But radon is not the only way uranium's presence in the environment touches human health in ways that most people do not think about. Uranium also dissolves in water. Not easily, and not in large quantities, but groundwater that passes through uranium-bearing rock picks up trace amounts of the element and carries it into wells, springs, and water supplies. In some regions, naturally occurring uranium concentrations in drinking water exceed the levels that health authorities consider safe for long-term consumption. Parts of Finland again, parts of Canada, regions of India, and various locations across the American West and Southwest have been identified as areas where groundwater uranium concentrations require monitoring and in some cases treatment. And here the story takes a turn that surprises many people, because the health risk from uranium in drinking water is not primarily radiological, it is chemical. Uranium is a heavy metal, and like other heavy metals, it is chemically toxic to the kidneys. At the concentrations found in affected groundwater sources, the primary concern is not the radiation the uranium emits, which at those levels is modest, but the same kind of toxic accumulation in kidney tissue that makes lead and mercury hazardous. Long-term consumption of water with elevated uranium concentrations is associated with kidney damage that develops gradually over years, and in populations that have relied on contaminated wells for generations without knowing it, the damage may be widespread and chronic before anyone identifies the cause. There is also a pathway that almost nobody thinks about, but that represents a real, diffuse, long-term alteration of the background uranium in agricultural soils. Phosphate fertilizers, which are used globally in industrial agriculture to supply crops with the phosphorus they need to grow, are derived from phosphate rock, specifically from mineral deposits called apatite. Apatite is a calcium phosphate mineral, and it is a good host for uranium in the crystalline lattice, which means that phosphate rock deposits are often uranium-bearing. When phosphate rock is processed into fertilizer, some of the uranium remains in the product, and when that fertilizer is spread on agricultural fields year after year, the uranium accumulates in the soil. The process is gradual. Annual additions are small, but over decades of intensive fertilizer application, the uranium concentration in agricultural soils and heavily farmed regions has measurably increased above natural background levels. Plants take up uranium from soil, primarily through their root systems, and while most edible crops accumulate only tiny amounts, the presence of uranium in food is real and, in areas of high fertilizer use, higher than it would be in unfertilized soil. The concentrations involved are generally far below levels of acute concern, but they represent a slow, invisible, multi-generational change in the chemical environment of agricultural land, a change that is largely unmonitored and that has no obvious stopping point as long as phosphate fertilizers continue to be manufactured from natural apatite. Uranium, element number 92, is not a material that exists only in reactors and warheads and mines. It is present in the air of certain homes. It is dissolved in some people's drinking water. It is on the fields that grow some of our food. It is in the smoke detectors of a different kind than the one you might check your battery on, though that is a different isotope and a different application. It is dispersed at trace levels through the living environment of contemporary civilization, not as a consequence of nuclear accidents or weapons programs, but simply because it has been in the rock of this planet since the planet formed. And rock weathers, and water flows through it, and gas escapes from it, and fertilizer carries it onto fields, and life goes on inside it, and around it, and despite it. This is not cause for panic. The concentrations involved in normal daily life are low, the risks incremental rather than acute, and for most people in most places, the background exposure to environmental uranium represents a negligible contribution to their overall health risk compared to factors like smoking, diet, and physical activity. But it is a reminder that the element we have been describing through the grand arc of cosmic creation and planetary geology and wartime physics and energy policy is also, quietly and without drama, part of the texture of ordinary life. Uranium has been here the whole time. It was here before us. It will be here after us. We are the visitors. It is the permanent resident. There is a particular kind of historical irony that requires a certain emotional distance to fully appreciate. The kind of irony that would be funny if its context were not so heavy with consequence. In 1993, the governments of the United States and the Russian Federation signed an agreement that has come to be known informally as Megatons to Megawatts. The formal title was the Agreement between the Government of the United States of America and the Government of the Russian Federation concerning the disposition of highly enriched uranium extracted from nuclear weapons. What it agreed to do was this. Over the course of 20 years, 500 metric tons of highly enriched uranium, the fissile material extracted from approximately 20,000 dismantled Soviet nuclear warheads, would be diluted down from weapons-grade enrichment levels of 90% or more to reactor-grade levels of less than 5% and sold to the United States Enrichment Corporation for use as fuel in American commercial nuclear power plants. 500 tons of weapons uranium, 20,000 warheads worth of material. The very same highly enriched uranium that had been manufactured at enormous cost and with extraordinary engineering effort to be placed atop intercontinental ballistic missiles and aimed at American cities was to be mixed with depleted uranium, reduced to the concentration at which it could power a reactor but not sustain a supercritical explosion, and fed into the fuel supply of the civilian electricity grid. And this program ran for 20 years, from 1993 to 2013, and it worked. By its completion, roughly 10% of the total electricity generated in the United States during those 2 decades had come from the combustion of former Soviet warheads. In some individual years, the fraction was higher, approaching 13 or 14% of total American electricity generation. Every time someone in the United States turned on a light switch, charged a phone, ran a washing machine, or kept a hospital running during those years, there was a real statistical probability that some fraction of the electricity powering that act had come from an object that, not long before, had been part of a nuclear arsenal aimed at the country consuming it. This is not a metaphor. It is not a figure of speech. The photons illuminating American living rooms in the 1990s and 2000s were, in a traceable physical sense, generated by the controlled fission of uranium that had been removed from warheads built to destroy American cities. The swords were beaten into plowshares, the missiles became megawatts, and almost nobody noticed. The program was real, significant, economically substantial, and almost entirely absent from public consciousness. Most Americans who benefited from it had no idea it existed. But uranium's capacity for transformation does not end at the boundary between destruction and electricity generation. It extends into something far more intimate: the human body and the technology we use to understand what is happening inside it. When uranium fissions in a nuclear reactor, it produces a range of radioactive isotopes as byproducts, and some of these isotopes are not waste products to be managed and contained, but extraordinarily useful tools for medical diagnosis. The most important of these, in terms of current global medical practice, is molybdenum-99, a fission product that decays into technetium-99m, the lowercase m standing for metastable, a short-lived nuclear excited state. Technetium-99m has a half-life of 6 hours, which is short enough that it disappears from a patient's body within a day or two after administration, minimizing radiation exposure, but long enough to be useful in the time frame of a diagnostic procedure. It emits gamma rays at an energy that is ideal for detection by medical imaging equipment. It can be chemically attached to a wide range of biological molecules that target specific tissues and organs, allowing physicians to visualize blood flow to the heart, bone metabolism, kidney function, thyroid activity, lung perfusion, and brain function with a precision that no other technique can match. Every year, approximately 40 million nuclear medicine procedures using technetium-99m are performed worldwide. These are not exotic or experimental treatments available only at research hospitals. They are routine diagnostic procedures conducted at ordinary hospitals and clinics on every inhabited continent, used to diagnose heart disease, detect bone metastases, evaluate kidney function before transplant, identify pulmonary embolism, and perform dozens of other clinical assessments that directly influence treatment decisions and save lives. 40 million times a year, a radioactive isotope produced by the fission of uranium in a research reactor is injected into a human body for the purpose of seeing something that would otherwise be invisible. Something that, if missed, might be fatal. The irony that the same physical process, uranium fission, that produced the weapons of Hiroshima and the Cold War arsenals also provides the isotope that allows oncologists to detect the spread of cancer in a living patient is almost too pointed to absorb without a moment of stillness. And uranium's reach extends further still, past medicine, past energy, past everything on this planet, into the darkness between worlds. The radioisotope thermoelectric generators that have powered some of the most important spacecraft in the history of planetary exploration, including the Voyager 1 and Voyager 2 probes, the Cassini mission to Saturn, the New Horizons probe that flew past Pluto, and the Curiosity and Perseverance rovers on Mars, run on plutonium-238, an isotope that does not occur naturally in significant quantities on Earth, but is manufactured in nuclear reactors from uranium-238 through neutron capture and subsequent decay. Plutonium-238 decays by alpha emission with a half-life of 87.7 years, generating a steady, reliable heat that can be converted to electricity by thermoelectric devices. In the cold, dark, radiation-bathed environments of deep space, where solar panels cannot function because sunlight is too faint or too inconsistent, plutonium-238 RTGs have provided decades of continuous power with no moving parts, no maintenance, and no possibility of refueling. Voyager 1 was launched in September 1977. It crossed the heliopause, the boundary between the solar wind and interstellar space, in 2012, becoming the first human-made object to leave the solar system. At the moment this script was written, it is more than 23 billion kilometers from the Sun, traveling outward at approximately 17 kilometers per second. It is still transmitting. Its signal, a whisper of radio waves crossing an almost incomprehensible distance, is still received by the deep space network antennas on Earth. And powering those transmitters, providing the electricity that keeps the scientific instruments running and the signal flowing across more than 20 billion kilometers of void, is the heat from the decay of plutonium-238, manufactured in a nuclear reactor from uranium that was mined from the Earth, processed by human hands, and transformed into a power source that is now traveling through interstellar space. From the rock of Oklo, from the waste heaps of the Ore Mountains, from the laboratories of Paris and Berlin, from the desert of New Mexico, across the boundary of the solar system, one element, one story, spanning from the moment of its creation in a neutron star collision to the edge of everything we have ever explored. There is a technique that geologists use to determine the age of ancient minerals, and it is so elegant, so precise, and so deeply revealing that it deserves a moment of genuine admiration before we use it to close this story. The technique is called uranium-lead dating, and it works because of a property of uranium that we have been circling around for every chapter of this account: the absolute, unvarying, clock-like regularity of its radioactive decay. When a zircon crystal forms from molten rock, whether in a cooling magma chamber deep in the crust or in the violent heat of a meteorite impact, it incorporates uranium into its crystal structure readily because uranium's ionic radius fits comfortably into the lattice sites that zircon normally reserves for zirconium. But zircon has a strong chemical aversion to lead. It essentially refuses to incorporate lead when it crystallizes. This means that any lead found inside a zircon crystal today was not there when the crystal formed. It got there later. It got there because uranium atoms inside the crystal decayed, step by step down their radioactive decay chains, and eventually reached the stable lead isotopes that are the final products of those chains. Uranium-238 decays to lead-206 with a half-life of 4.468 billion years. Uranium-235 decays to lead-207 with a half-life of 703 million years. These are constants. They do not change. Temperature does not affect them, pressure does not affect them, chemical environment does not affect them. The geological history of the rock does not affect them. From the moment the zircon crystal locks its uranium in and excludes lead, the clock starts running. Every million years, a precise and calculable fraction of the uranium decays to lead. By measuring the ratio of uranium to lead in a zircon crystal today, using mass spectrometry instruments sensitive enough to measure the isotopic composition of a grain of mineral smaller than a grain of sand, geologists can calculate, with extraordinary precision, exactly how long ago that crystal formed. Using this technique on tiny zircon grains recovered from ancient sedimentary rocks in the Jack Hills of Western Australia, scientists have determined that the oldest mineral grains yet found on Earth formed approximately 4.4 billion years ago, just over 100 million years after the formation of the solar system itself. These are not fragments of the original planet, the surface of which was entirely molten and reset multiple times in the early solar system. They are grains that crystallized as the first solid crust began to form on a cooling Earth, trapped in later sedimentary rocks and preserved through billions of years of geological recycling. They are the oldest physical objects of terrestrial origin that have ever been held in a human hand. And we know how old they are because of uranium. The same technique applied to meteorites, which preserve some of the oldest material in the solar system without the complications of planetary geological processing, gives an age for the formation of the solar system of 4.567 billion years, with a measurement uncertainty of less than 1%. This is one of the most precise dates in all of science. We know the age of our solar system, the age of our planet, and the minimum age of the oldest terrestrial rocks, not because of carbon dating, which works only for organic materials less than 50,000 years old, not because of any historical record, and not because of any theoretical calculation, but because uranium decays at a known, constant rate and leaves a measurable trace of lead behind it in the minerals it inhabits. The universe handed us a clock with a known tick rate and then put it in the rock. We needed only to learn how to read it. And so we arrive at the end of this story at something that feels, in its way, like a kind of completion. Uranium was born in the collision of two neutron stars, an event so violent it bent space-time. It traveled through the galaxy as part of a dispersing cloud of heavy elements mixed into the nebula that became our solar system and settled into the rock of the forming Earth. For 4.5 billion years, it has been doing what it does, decaying, releasing heat, powering the planet's interior, driving the tectonics and the volcanism and the magnetic field that makes this world habitable. For 4.5 billion years, it has been leaving behind, in every mineral that incorporated it, a perfect record of time. Right now, as you hear this, approximately half of the uranium that was originally in the Earth when it formed is still here, still decaying, still releasing heat, still keeping the inner fire burning. The other half has become lead, quietly, atom by atom, over geological time. In another 4.5 billion years, half of what remains today will also have become lead. The process will continue, according to its own unalterable schedule, without reference to anything we do or do not do, long after every city we have built has been erased by erosion, long after every language we have spoken has been forgotten, long after the species capable of writing this sentence has been replaced by whatever comes next. In the 235 years since Martin Klaproth looked at a piece of pitchblende and saw something he did not recognize, we have learned an enormous amount. We have learned where uranium comes from. We have learned how it powers our planet. We have learned how to split it and how to burn it, and how to use the products of its fission to see inside living bodies and to propel machines through interstellar space. We have used it to destroy entire cities in seconds and to light homes for generations. We have used it to measure the age of the solar system to within 1%. We have learned that it causes cancer when we breathe it unknowingly, and that it was protecting the conditions for life long before any life existed to be protected. What we have not fully learned yet is what to do with the obligation it has given us. The radioactive waste that will outlast our languages, the warheads still pointed at cities, the radon seeping through foundations that nobody has tested, the slow accumulation of uranium in agricultural soils. These are not problems that uranium created. They are problems that we created by extracting uranium from its geological context and concentrating it, purifying it, and using it in ways that require us to then manage the consequences across timescales our institutions were never designed to handle. The element does not wait for us to figure this out. It does not accelerate or slow its decay based on whether we are ready. It is not indifferent in any meaningful sense because it is not capable of indifference. It simply is what it is, a remnant of stellar violence, a source of planetary heat, a clock running in the rock, a tool we have barely begun to understand how to use responsibly. The question of what we do with it, how we manage the waste, whether we use it for power as the climate crisis deepens, how we ensure that the most destructive concentrations of it are never used again. These are the questions that will define how the story of uranium continues. They are not scientific questions at their core. They are questions about what kind of civilization we choose to be. about whether we are capable of thinking on timescales longer than an election cycle or a business quarter, about whether we can be adequate stewards of something this powerful and this permanent. Uranium has been patient for 4.5 billion years. The patience is not on our side.
The time we have to make these decisions, measured against the half-life of the element that made them necessary, is barely the blink of a geological eye. Element number 92 does not need us, but the future that contains us will be shaped, in no small part, by what we decide to do with it now.